Good afternoon and welcome back to Dr. Logic Does. I awkwardly do logic. You'd think I would know how to say that by now. Anyway, last time we finished off with a quick little corollary, which was the last of all of the technical bits that we need in order to actually deploy the canonical models method that we have been working towards for like 5 years now. So well done, all of you who've managed to stick it out this far. I promise you, we're getting close. What I want to do in this video is just kind of talk us through the concept of how the method works, because this is the part that is the most difficult. The technical stuff, yeah, it's all just like symbol pushing. Understanding what we're doing and why we're doing it and how all of this works can be the tricky bits. So hopefully it will be a little bit clearer after this video before we go on to actually applying the method. So remember, completeness. You've got a class of models and you have this generates a list of all of the formulas that are going to be true at every world, in every one of these models, no matter what valuation you have. We want to show that a class like that corresponds to some logical system where you've got axioms, rules of inferences, and then everything that you can derive from those. So completeness takes a bunch of models and says everything that is valid in these models can also be derived in the corresponding system. So that system is then complete with respect to those sets of models. Now, what we have done with the canonical model is something really cool. We have constructed a model that every theorem is going to be valid in that model, and no non-theorem is going to be valid. Because for every non-theorem, we can find a possible world, a maximal consistent set, where that theorem is false, where that formula is not a member of the world. So this feels like we're very close. All of the theorems are valid in the model. All of the non-theorems are not valid. What we need is something that gets us from that single model to a class of frames. Because most of the systems that we've looked at so far have been characterized by a class of frames. For instance, the logic of K is the logic of everything on any frame, no frame conditions whatsoever. Logic of T, the logic of reflexive frames. D, serial frames. S4, transitive and reflexive frames. B, symmetric frames, and so on. So we've got these frame conditions, whereas what we have with the canonical model is a model. Now, the thing about models is that I can do lots of models where on that particular model, because of how I put the worlds together and how I've defined the valuation, it might just so happen to turn out that, for instance, the B axiom is true at every world on that model. But that's not enough. Because what if I change the valuations? I might be able to falsify it. This is why the frame correspondence, the correspondence between axioms and frame properties is so important, so that the only time that you know that an axiom is valid on the frame is if it's got the right kind of properties. So the issue is that frame correspondences and the characterizations of logic is happening at the level of frames, which can have multiple different models, whereas the canonical model is just a model. However, if I can show that the frame that underlies the canonical model is a frame for the logic, then I'm done. So if the canonical model for, say, system B is based on a reflexive frame, then I have something that shows I can prove all of the theorems. They're all valid on this frame, which is a frame for the logic. And I have a counterexample to everything that is a non-theorem, so everything that we can't prove. This is what we need. Now, in some cases, this is easy. In the case of K, our model is based on a frame. K is characterized by the class of all frames. Therefore, the canonical model is a frame. It's based on a frame. That's all good. Don't worry. I'll say this again in the next one as we start going through the results systematically. But why Why would we think that, for instance, the canonical model for S5 is reflexive, transitive, and symmetric? We don't have an in principle reason to think that this is the case. This is something that we need to systematically go and show. So what we will do is we will give a couple of examples of how this works, how you actually show that the frame of the canonical model is a frame for the logic in question, which then kind of completes what we need to show that the system is complete. And if we have time, and it doesn't take another 5 years, I may also show you a system which is complete, but where the frame underlying the canonical model is not a frame for the logic. So there are some non-canonical logics out there, which are super fun, but also we've been doing this a long time. There's other things I want to talk to you about. We may or may not get to it. In any case, I hope this gives you a sense of like what the whole process is. We will take the canonical model for a particular logic, and we will show that the frame that underlies that model is a frame for that logic. And that will be what we need to prove our completeness. So next video, we'll do this for K, and we'll probably also do it for another one, maybe D or T, because K is so stupidly easy, it won't actually teach you anything. So join me again. We're almost there. Looking forward to see you again soon. Cheers.